What if I told you that no matter how you define a mathematical space, the number of fundamental building blocks required to describe it is always the same?
Dr. Akira, are you talking about dimensions again? I always get a bit lost there.
Yes, Hasan, precisely. But not just any dimensions. We are talking about the true dimension of a vector space. It is a beautiful concept, I promise. For centuries, mathematicians wrestled with this very idea. If a vector space can have multiple bases, different collections of vectors that span the entire space, how can we be absolutely sure that the number of vectors in each of those bases is always identical? It does feel a bit counterintuitive at first, doesn't it? Like suggesting a 3D space could somehow be defined by only two directions.
It really does, Dr. Akira. It's one of those things that just doesn't click for me right away.
And that's perfectly normal, Hasan. But why and how do we prove such a magnificent universal truth? That, my dear student, is what we will unravel together today. The glorious proof of the uniqueness of dimension.
So, if I understand correctly, a basis for a vector space V over a field F is a set of linearly independent vectors like V1, V2, and so on, and Vn, that also spans V. This means any vector in V can be written as a unique linear combination of those basis vectors. Is that the part where it's like a minimal set of directions?
Excellent, Hasan. You've got the core idea. Think of it like the x, y, and z axes in our familiar 3D world. They are independent and they can describe any point in that space. But then the question arises, what if we chose a different set of 3 vectors, or perhaps 2, or even 4?
And the number of vectors in a basis is what we call the dimension of V, denoted as dim_V. I remember that part. But it also says the dimension depends on the field F. That's the part that always trips me up.
A very keen observation, Hasan. The field is indeed a crucial detail.
So, for example, complex numbers C can be one-dimensional over themselves, with 1 as a basis. But over the real numbers R, it's two-dimensional with 1 and I is the imaginary unit. That still confuses me sometimes. How the size changes just by changing the field.
It's a subtle point, Hasan, but you are grasping it. Now the grand question remains. If we have two different bases for the same vector space, say v1 up to vn and w1 up to wm, how do we prove that n must equal m?
This is Theorem 1, the uniqueness of dimension. And to prove it, we'll use something called Lemma 2.
Yes, the exchange lemma. It's a truly elegant piece of mathematical machinery that makes the main proof possible.
So, if I'm reading this right, it means we can swap out a vector from one basis with a vector from another, and the new set will still be a basis for the same space. That sounds powerful.
It is, Hasan. Let's dive into the proof of this magnificent lemma. Imagine the subspace W is spanned by V1 up to Vn and also by W1 up to Wm. We'll assume, for simplicity, that we are replacing V1.
Step 1. Show the subspace U spanned by V2 up to Vn is a proper subset of W. If U is equal to W, then V1 would belong to U, so it should be a linear combination of V2 up to Vn, making V1 up to Vn linearly dependent. But it's a basis, so it must be linearly independent. This is a contradiction, so U is a proper subset of W.
Precisely. A contradiction is a powerful tool in proofs.
Step 2. Find a Wj not in U. Since U is a proper subspace of W and W is spanned by W1 up to Wm, at least one Wj must not be in U. Otherwise, the subspace spanned by W1 up to Wm is a subspace of U, which would mean W is a subspace of U. Another contradiction. We can reorder so W1 does not belong to U. Now, the set W1, V2, V3, and so on up to Vn is linearly independent. If it weren't, W1 would be a linear combination of V2, V3 up to Vn, meaning W1 is in U, which we just showed is false. Oh, I see. So we have to find a Wj outside of U, otherwise the whole linear independence falls apart for the original basis.
Very good, Hasan. You found our replacement vector.
Step 3. Show the subspace W prime spanned by W1, V2 up to Vn is equal to W. Since V2 up to Vn are in W and W1 is in W, it's clear that W prime is a subspace of W. Now, for the other direction, we know W1, V1, V2 up to Vn are linearly dependent because W1 is in the subspace W, which is spanned by V1, V2 up to Vn. Since W1, V2 up to Vn is linearly independent, it must be that V1 that can be expressed as a linear combination of W1, V2 up to Vn. This means V1 is in W prime. Since every Vi is now in W prime, it implies W is a subspace of W prime. Therefore, W prime is equal to W. We've successfully swapped V1 for W1 and kept the same span and linear independence.
Bravo, Hasan. You following along wonderfully. The exchange lemma proven in all its elegance.
So, with Lemma 2, proving Theorem 1 should be easier. Suppose V has two bases, V1 up to Vn and W1 up to Wm. We can assume n is less than or equal to m without losing generality.
That's a clever trick in mathematics, Hasan. The power of assumption.
We use Lemma 2 repeatedly. First, we replace V1 with some Wj1 from the second basis, forming a new basis, Wj1, V2, V3 up to Vn. Next, we replace V2 with some Wj2, giving us Wj1, Wj2, V3 up to Vn. We continue this n times. After n swaps, we will have a new basis for V, Wj1, Wj2 up to Wjn. This new basis consists entirely of vectors from the original W1 up to Wm set.
A complete transformation. You are doing great, Hasan.
Now, here's where I might get stuck. What if n is strictly less than m? This means there's at least one Wk from the original W1 up to Wm set that wasn't used in our basis Wj1 up to Wjn.
Keep going, Hasan. You're almost there. Think about what would imply for the set Wj1, Wj2 up to Wjn and Wk.
Since Wj1 up to Wjn is the basis for V and Wk is in the vector space V, then Wk must be expressible as a linear combination of Wj1 up to Wjn. This means the set Wj1, Wj2, Wjn, and Wjk is linearly dependent, right?
Absolutely correct.
Aha. But wait, on the other hand, The set wj1, wj2, wjn, and wk is a set of the original bases from w1 to wm. And by definition, a basis is a set of linearly independent vectors. So any subset of a linearly independent set must be also linearly independent. This means the set is both linearly dependent and linearly independent. That's a contradiction. It cannot be both. That's the key.
Precisely, Hasan. Glorious, beautiful contradiction. It means our initial assumption that n is strictly less than m must be false. Therefore, n must equal m. You've done it. You've truly grasped the core of it. And there you have it, Hasan. The magnificent proof that the dimension of a vector space is unique. No matter how many different bases you find, the number of vectors in each will always be the same. It's a fundamental property, a universal constant for that particular space.
So, this theorem is crucial because it allows us to define the dimension of a vector space unambiguously. It's not just a number we pick. It's an intrinsic property. I really think I finally get it now. It's like the space itself dictates how many fundamental directions it needs, no matter how we choose to label them. The contradiction makes it so clear.
You certainly do, Hasan. Think of it. Whether you describe a point in 3D space with Cartesian coordinates or spherical coordinates or cylindrical coordinates, you always need 3 independent values. 3 is the dimension, the very essence of its spatial being.
Understanding this concept really does feel foundational for advanced topics in linear algebra, differential equation, and even quantum mechanics. Thank you, Dr. Akira. This really helped.
My pleasure, Hasan. So go forth, my aspiring scientist. Explore the dimensions, unravel the mysteries of the universe, one vector space at a time, and remember, the number always stays the same.
And that's all for today. Don't forget to like, subscribe, and hit that notification bell for more mathematical adventures with Dr. Akira and me.